The U.S. Air Force ignited a hydrogen-fueled jet engine, pushed it through high-temperature burn tests, and proved it could deliver combat-class thrust without a drop of jet fuel. No kerosene, no tanker dependency. The engine sustained stable combustion and achieved efficiency conventional propulsion can't match. While adversaries extend missile range and field hypersonic platforms, the real bottleneck isn't weapons, it's fuel. Hydrogen propulsion doesn't just promise cleaner exhaust. It threatens to rewrite range, endurance, and logistics in a future fight. What unsettles China isn't the engine. It's what happens when American air power no longer depends on vulnerable fuel lines across the Pacific. How jet engines work. Traditional jet engines have ruled the skies for more than half a century, powering everything from early military fighters to the huge airliners that connect distant continents. At their heart is a simple, relentless cycle. Air is sucked in, crushed down to high pressure, mixed with fuel and burned, and blasted out the back at astonishing speed. That blast is what pushes the aircraft forward. First, the engine's giant fan and compressor blades grab huge amounts of air and squeeze it tighter and tighter. This compression greatly increases its pressure and temperature, setting the stage for the next act. In the combustion chamber, carefully measured fuel is sprayed into this compressed air and ignited. The explosion is a continuous, controlled burn that forms scorching, high-energy gas. From there, the hot gas races through the turbine, a set of blades that looks like a spinning windmill. The turbine steals a portion of that explosive energy to turn the compressor at the front. It's this clever recycling of power that lets the engine run continuously without dying out. What's left of that superheated gas doesn't just drift away. It shoots out the exhaust at speeds that can exceed the aircraft's forward motion, and in doing so, tugs the airplane forward by the unyielding law of physics. For every action, there's an equal and opposite reaction. These engines define 20th century flight, but as engineers looked for cleaner, faster, and more efficient systems, this classic power plant is starting to feel like the opening act of a technological revolution. But before we discuss this new hydrogen jet engine, don't forget to subscribe to our channel for more coverage on the U.S. Air Force and its latest weapons, birth of the jet age. Long before hypersonic dreams and hydrogen power, two brilliant minds quietly changed the world of flight forever. In the 1930s, Sir Frank Whittle, a young Royal Air Force engineer in Britain, sketched out an idea that sounded radical at the time. What if an aircraft didn't need big, heavy propellers, but could instead be pushed forward by a stream of fast-moving gas generated inside a new kind of engine? Whittle patented the first workable turbojet design in 1930 and spent years pushing it forward, despite skepticism and funding struggles. His early prototype, tested in 1937, proved the concept could work, even if it was still rough around the edges. Meanwhile, in Germany, another engineer named Dr. Hans von Ohain was thinking along the same lines. Working with aircraft builder Ernst Heinkel, von Ohain developed his own jet engine design, and by the late 1930s, he made something that actually flew. On 27 August 1939, the experimental Heinkel He 178 took to the air, becoming the world's first jet-powered aircraft. This was a moment that stunned aviation pioneers everywhere. Whittle's own breakthrough came soon after. In May 1941, his Powerjet's W1 turbojet was installed in the Gloucester E-28/29, the first British aircraft powered by a Whittle engine, and it soared into history on its maiden flight. These early engines and prototype aircraft opened a door to the jet age. This quickly became the foundation for all modern high-speed aviation, from fighters and bombers in World War II to the massive airliners that now define global travel. Jet engines were no longer limited to military use. But how did this new technology become the basis for global use? Shift to commercial use. After World War II, jet engine technology didn't stay confined to fighters and bombers. The same power that had helped win battles was soon turned into something that would change everyday life, and that was commercial passenger air travel. The first real breakthrough came with Britain's de Havilland Comet, which first took to the skies in 1949 and entered airline service in 1952 as the world's first commercial jet airliner. It could cruise higher and faster than the piston-powered plane that came before, giving passengers a smoother, quieter flight and dramatically shorter journey times. Although early models suffered structural issues and were temporarily grounded, the Comet eventually proved that jet engines belonged outside of the military and opened the door for a new era of flying. But it was the arrival of the Boeing 707 that ignited the jet age for commercial travel. After its first flight in 1957, the 707 entered service in 1958 with Pan American World Airways, flying passengers from New York to Paris at speeds and altitudes previously unheard of in civilian travel. It was faster, more comfortable, and could carry many more people than the old propeller aircraft, helping jet travel quickly become the norm on long-distance routes. Almost at the same time, the Douglas DC-8 joined the race, giving airlines another powerful and capable jet to choose from as they retired their piston engines. Together, the 707 and DC-8 did more than just replace old technology, cutting off hours from intercontinental flights and making international travel something ordinary people could imagine and afford. These early jetliners connected the world in ways that had never been possible before, but they eventually evolved for better use in the military. Rise of turbofans. As air travel became more common, engineers quickly realized that the early jet engines, the turbojets, were powerful but thirsty and noisy. When looking for a better way to fly, a new breed of engine emerged, and that's the turbofan. Unlike its predecessors, a turbofan doesn't depend only on burning fuel to push a narrow jet of hot gas out of the back. Instead, most of the air it draws in at the front travels around the engine core through a large fan, creating a new source of push that doesn't require burning extra fuel. This clever shift makes turbofans dramatically more fuel efficient and quieter, making them the backbone of modern commercial aviation. In simple terms, a turbofan splits the incoming air into two streams. One goes into the core to be compressed, mixed with fuel, and burned, and another rushes around the outside. Because this bypassed air moves a large mass of air at a lower speed, the engine produces thrust more efficiently and uses less fuel than older designs. Two modern engine families show how far turbofan technology has come. The CFM56 series, one of the most widely used commercial engines ever built, powered generations of Boeing and Airbus jets, balancing reliability with strong performance. More recently, Pratt & Whitney's PW1000G geared turbofan introduced a breakthrough gearbox that lets the large fan and the turbine spin at their ideal speeds. This squeezes out up to 16% better fuel efficiency and much quieter operation than the older engines. Thanks to these advances, turbofans have reduced airline fuel costs, cut noise pollution, and helped make flying a normal part of life. Around the world, the turbofan engines became a defining pillar of modern aviation, transforming commercial flight with efficiency and range. But the military didn't stay behind. It evolved its own class of high-performance engines, now powering frontline fighters and bombers like the F-35. So how did these new military engines go beyond traditional turbofans and open the door to an entirely new generation of propulsion? The Pratt & Whitney F-135. When looking at the engines that power the cutting edge of military aviation, there are few names that carry as much weight as the Pratt & Whitney F-135. It's the heart of the Lockheed Martin F-35 Lightning II, the United States and Allies' premier fifth-generation fighter jet. Designed in the 2000s and entering production later that decade, the F-135 was built to give the F-35 unmatched performance, reliability, and flexibility across a wide range of missions. What makes the F-135 remarkable is how it balances raw power with adaptability. At its core, it's an afterburning turbofan, meaning it blends efficient cruising with a huge burst of thrust available when fighters need speed or agility the most. The engine can deliver well over 40,000 pounds of thrust when its afterburner kicks in. It's enough to push a supersonic fighter through the sky with blistering acceleration. The F-135 family comes in three main variants tuned for the different versions of the F-35. There's the F-35A for conventional takeoff and landing, the F-35B designed for short takeoff and vertical landing, and the F-35C optimized for aircraft carrier operations. Each variant uses the same powerful core, but it is slightly modified to meet the specific needs of its branch of service. from the Marines' amphibious assault ships to the Navy's carrier decks. But power isn't the whole story. The F-135 also features advanced digital controls that constantly adjust performance for efficiency and responsiveness, making it one of the most modern and dependable fighter jet engines ever produced. Its design supports stealth features and helps the F-35 perform in contested battle spaces where every ounce of thrust and reliability counts. While traditional jet engines have powered both commercial and military aviation for decades, forming the backbone of modern flight, the real breakthrough is the technology poised to take propulsion beyond those limits. The U.S. Air Force and its partners are now advancing next-generation hybrid and hypersonic systems like the Chimera engine, a turbine-based combined cycle design that starts like a conventional jet and transitions into ramjet performance at extreme speeds. Instead of relying solely on a compressor turbine loop burning kerosene, Chimera blends turbine and ramjet capabilities to operate efficiently from takeoff all the way to hypersonic flight. That shift could open the door to revolutionary aircraft concepts powered by hydrogen or advanced fuels, reaching speeds once reserved for rockets and transforming both military and civilian aviation. So what exactly is Chimera, and how could it redefine the future of flight? If you're still watching, you're clearly into this. Do me a favor, hit the like button, subscribe to the channel, and let me know in the comments, what do you think will matter most in the race for hypersonic propulsion? The Chimera engine. Imagine an engine that doesn't just push air and fuel through a single cycle, but changes how it works on the fly. That's the promise of the Chimera engine, a cutting-edge design from the aerospace company Hermeus that could redefine what it means to power flight. Unlike traditional engines that are limited by their mechanical design, Chimera is a turbine-based combined cycle power plant, blending a turbojet with a ramjet to cover a far wider range of speeds than either could on its own. At low speeds, Chimera behaves like a jet engine, using a turbine to compress air and burn fuel to generate thrust. But as the aircraft accelerates, the air rushing in becomes so fast and hot that the turbine engine starts to lose efficiency. Chimera's clever design redirects incoming air around the turbine and activates a ramjet mode, which doesn't need moving parts to compress air, but instead uses the aircraft's speed to force air through the combustion process. This smooth transmission from one mode to the other was successfully demonstrated on the ground. This is a technical milestone in the quest for practical hypersonic flight. This flexibility could let future aircraft take off from a normal runway and climb up to hypersonic speeds without rockets, a capability most hypersonic prototypes today still don't have. Rocket engines can reach extreme velocities, but they are expensive, often one-time use, and tough to handle. Chimera's air-breathing approach aims for reusable, rapid turnaround flight. It's more like today's jets than today's space launch hardware. There are two aircraft programs that illustrate Chimera's potential. The first is Quarter Horse, a high-speed demonstrator designed to validate the engine's performance and gather flight data on rapid acceleration and propulsion transitions. The second is Dark Horse, a hypersonic unmanned aerial system powered by an enhanced Chimera 2 engine that integrates a proven Pratt & Whitney F-100 core to kick off the turbine mode before the ramjet takes over. For aviation and defense alike, Chimera is a bridge between subsonic jets and true hypersonic flight, pointing toward a future where aircraft can travel in minutes what today takes hours. But the Chimera isn't the only advancement that the USAF has made in hydrogen, propulsion, and engines. It has emerged with a plan to study hydrogen electric propulsion for their autonomous aircrafts. Hydrogen electric flight. The future of flight is now about flying cleaner, quieter, and smarter. That's where hydrogen electric propulsion comes in, a technology that mixes the best parts of hydrogen fuel and electric motors to create a new kind of aircraft power plant with the potential to change how military and civilian aviation operate. In 2025, the U.S. Air Force's innovation arm, AFWERX, took a major step in this direction by awarding a small business innovation research grant to the aviation startup ZeroAvia to study how hydrogen electric propulsion could be integrated into an autonomous aircraft. This project focuses on turning what seems like science fiction into a real capability. They look to create a plane powered by hydrogen fuel cells and electric motors instead of a traditional internal combustion engine. Hydrogen fuel cells work by converting hydrogen into electricity with zero carbon emissions, and that electricity then drives electric motors that turn the aircraft's propulsors. This setup offers high specific energy, meaning a great amount of energy for relatively little weight. It's a huge aircraft in aircraft design. The planned aircraft for the study is a retrofitted Cessna Caravan, a rugged workhorse airplane whose hydrogen electric powertrain, called ZA600, produces about 600 kilowatts of power. Zero Avia and its partner, Reliable Robotics, will explore the propulsion system itself and how it integrates with autonomous flight systems. This enables future unmanned missions that require long range, low noise, and a low thermal signature. This has become a big advantage for military operations where detectability is important. Hydrogen has another important edge. It can be produced at the point of refueling using electricity and water, simplifying logistics for remote operations and reducing dependence on traditional fuel. Supply chains. That could be especially valuable in forward operating areas or disaster zones where fuel infrastructure is limited. The Air Force's interest in this feasibility study signals a major shift toward exploring sustainable and low-emission propulsion that delivers tactical advantages as well as environmental benefits. If this work proves successful, it could lay the groundwork for long-range, zero-emission autonomous aircraft that transform logistics, surveillance, and future air operations for decades to come, even before hydrogen electric power reaches passenger jets. Some aerospace companies partnering with the USAF are also conducting tests with hydrogen fuel. Industry hydrogen tests. Beyond the labs and prototype projects, the wider aerospace industry is pushing hard into hydrogen aviation research. One major player in this space is RTX, the parent company of Pratt & Whitney, which has been conducting advanced combustor tests using hydrogen fuel to explore how jet engines might one day run on clean, carbon-free power. In tests at the RTX Technology Research Center, engineers successfully burned hydrogen in a high-pressure combustor rig designed to simulate real engine conditions, proving that hydrogen can be burned safely, stably, and without destroying engine parts. These tests are part of a program called HySci-ITE, Hydrogen Steam Injected Intercooled Turbine Engine, which also showed large reductions in harmful nitrogen oxide emissions and improved energy efficiency, suggesting hydrogen could be a transformative aviation fuel for the industry. Race for clean flight. The world is pushing for cleaner skies, and aviation is at the forefront of a major shift toward less polluting propulsion systems. Traditional jet engines burn kerosene-based fuels and emit large amounts of carbon dioxide, and are joined by research into alternative fuels, hybrid systems, and advanced materials that could dramatically cut emissions and boost efficiency. One major focus is on sustainable aviation fuels, SAF, which are made from renewable sources and can reduce life cycle CO2 emissions by around 80% compared to conventional jet fuel, with research aiming to push that toward net zero carbon in the future. At the same time, engine makers like Rolls-Royce are investing heavily in hybrid electric propulsion technologies that could blend electric motors with traditional turbines to reduce fuel use and noise on short-haul flights. These hybrid systems are designed to give aircraft the benefits of electric drive, while overcoming battery limitations by using a small combustion generator to extend range. Another bold area of research is hydrogen combustion in jet engines. Recent ground tests by Rolls-Royce and airline partners have successfully run modern aero engines on hydrogen fuel, proving that hydrogen can be burned safely and efficiently in conditions similar to takeoff power. This experiment marked an important step toward a potential future, where hydrogen replaces fossil fuels entirely in certain aircraft engines. As hydrogen propulsion moves from laboratory testing to real military applications, the Air Force could be standing at the edge of a transformation as significant as the birth of the jet age itself. Longer range, reduced logistics risk, and entirely new aircraft concepts may soon reshape how air power operates in future conflicts. So what do you think will matter most? Extended endurance, hypersonic potential, or freedom from traditional fuel supply lines? Let us know your thoughts in the comments. And if you found this breakdown valuable, hit that subscribe button.